Hi everyone, and welcome to video number 12 of this series in which we are learning how to model an end plate steel connection. In this video, we are going to continue the post-processing procedure of this model in META. And well, I'm not sure if I'm going to use this whole video for that, but well, if we finish this post-processing quickly, then we can start creating the second version of this model that considers solid elements for the bolts, washers, and nuts. Okay. All right, so there are some things here that I wanted to show to you yet that are very important. In the previous video, we have learned about some things here in META. We have extracted this curve of moment versus rotation. We also extracted this to an Excel spreadsheet to compare this curve that we have calculated with experimental data. And then you see that there is some difference between the curve that we extracted and the one extracted from the experiment. This one that is a continuous black line. And also there is some difference if we compare with the results of the author's simulation. Well, I think that maybe one of the reasons why this is happening is because of the boundary conditions that we have considered. You see that in his model, notice that in this image, we have only half of the model considered. So he had used the symmetry condition to create this model. When we have the symmetry condition being used, in the symmetry plane that is not visible here in this image, he needs to apply some boundary conditions such as he needs to fix displacement in the y direction. Let's look at what is this direction. You see this coordinate system here, the y direction is this direction here. The y direction would be in the normal direction of the symmetry plane. When we have this displacement fixed in the y direction, we end up also restricting torsion in the beam. And also we end up restricting bending about the z-axis for the beam. Well, in this model that we had run, we didn't consider any of these boundary conditions. So one thing that we can do here is, and that I have done already, so let me do this again. Let me just undo one thing here. Let me see. Yep. Let me do this again because I have done this some minutes ago, and I also have put a new model to run. So in your ANSA model, open up Step Manager. And then here we have the 2 steps of our analysis. And on the second step, you see that we have this connector motion and boundary condition. Double click on boundary condition. And then we have only one item. We have this boundary condition, which is this displacement in the negative z direction applied to this node, right? We can double click to open it, and here we have it. Now I wanted to add one additional boundary condition at this same node to fix displacements in the y direction and also to fix some other degrees of freedom. So since I want to apply this boundary condition on the same node and at the same step, I'm going to get this one, right click and copy. So we have this boundary condition applied at the second step at this node, but the degrees of freedom are going to be displacement in the y direction, which is 2. I don't want this beam to rotate about the x-axis, that is torsion, so degree of freedom 4. And I don't want this beam to rotate about the z axis as well. So I'm going to constrain degree of freedom 6, which is rotation about z. And then in magnitude, we should have 0. Okay, guys, this is not exactly the same thing as we have in this module, because in this module, we have this condition for this whole symmetry plane. So this restriction is for the whole model. In here, we have this restriction applied only at the tip of the beam, which I think is more realistic if compared with the experimental setup. Because you see, in the experimental setup, where we have the load applied, we have this mechanism. This mechanism creates some resistance against a displacement in the y direction. Also, it creates some resistance against torsion of this beam, and also bending moments about the z-axis here. It doesn't completely constrain, as we are assuming here in our mathematical model. It creates some resistance. So you should think that this is a simplification. This is an assumption that we are assuming, and we should keep this in mind when we get to analyze the results. Because if we see that the results are a little different, then we can think that this is because of the assumptions that we have taken previously. So that's it. Click on OK. And now we have this additional boundary condition. We can close, and then we can go to File, Export, Output, Abaqus. And then you see that I have done this previously already. I have created this new .inp file, underline v2. So you can do the same, v2, save, and then you're going to end up having a new .inp file. If I double click on this new .inp file, I can go to search for step. Here you have the first step. Let me go to the next one, second step. And in the second step, I have this new boundary condition here. Okay, that's the difference. And then I can put it to run. To put it to run, open up cmd command on this folder, and then abacus job equals the name of the file and number of CPUs. And then I have done this, and this is running. Let me see here. So this is already in the second step, 37%. Okay. Well, I'm not sure if I'm going to post-process the results of this model in this video. I don't think so. I'm just going to post-process this offline, and then I'm going to show the new curve to you. And if you'd like, you can do this as well. Okay. All right. Let me see. I have spent 8 minutes. Guys, let's continue the post-processing of this model now, because there are some important things that I wanted to show to you yet. First of all, there is one very important step that we end up forgetting to go through. Let me go back to this presentation. This is the presentation that we have seen in the first course, in the linear FEA course. You see that this is from 2024. And well, this is the first video of all courses that I have related to FEA. This is where I define a physical problem, a mathematical model of the type boundary value problem. When I define domain, governing equations defined in the domain, and boundary conditions. So this is the definition of a BVP. I have defined what is a node, element, and etc. What is a domain? And what I wanted to show to you is this very important slide. This is extremely important, what we have here. So we know that in an FEA we have a physical problem, right, that we want to analyze. In this case, it's this problem. It's a problem of the real world. And then inside the FEA software, inside this box here, we are going to define a mathematical model of the type BVP, which is what we have done in ANSA. So we defined the domain, we defined the governing equations, and we defined the boundary conditions. We've done that by inputting some information in ANSA, right? And then we have used FEM to solve this mathematical model approximately. And then we found displacements at the nodes. This is the result that Abaqus calculates. And then we can post-process these results and calculate other results, such as the stress, the strain, reaction force, contact pressure, etc. Now, the thing is, we can use hand calculations or experimental data to compare with the simulation results. We have done this, right? And the name of this procedure is validation. In the validation procedure, we have a slide here for this validation. In the validation procedure, we check if the mathematical model that we have defined actually represents the physical problem. Because if it does, then the experimental data is going to match well with the simulation results. In our case, it's matching reasonably well. We have some differences here in the non-linear part, and we know that this is because of the assumptions that we have taken. Okay, we have some simplifications considered in the material modeling, in the boundary conditions, and etc. So, well, we can say that this BVP represents considerably well the physical problem. But we also have the verification procedure. In the verification procedure, we ask this question: did I solve the mathematical model correctly? Because one thing is to say, well, this BVP is representing well the physical problem, and another thing is to say this BVP is being solved correctly. So we need to check if this BVP was solved correctly, and this is named verification. And then we can do some things here. First of all, results consistent with a mathematical model. Guys, in the mathematical model, here in ANSA, when we defined this step, we used the static solver, right? When we do that, we define that there are the three equilibrium equations as governing equations defined in the domain of the problem, right? So this is part of the mathematical model. Now, to check if the results are consistent with this definition, we should check if in this model, the sum of all forces in all directions is equal to 0 as well, because we have these as governing equations. So I want to check if this was actually attended in this model. And this is a verification that we can always perform in a static analysis. Check if sum of all forces is equal to 0 in the x, y, and z directions. In this one, level of numerical errors acceptable. This is related to mesh convergence studies, and this is also related to the fact that we have used quality criteria for the elements to assure that numerical errors are acceptable. In theory, we would need to perform a convergence study, but as I mentioned in the meshing procedure, usually what the companies does is they have in their database, for example, for this kind of analysis, you can use element length equals 5 millimeters, because I already performed a convergence study and I know that this size of element is good enough for you to have convergence in your mesh. Okay, so in this case, I know that for this kind of analysis, 5 millimeters is good enough. So we are not going to perform this convergence study. Okay, but if you're building your on company, you should perform these for all kinds of analysis that you perform, and then you should store this information so that you don't need to do this over and over again in the future. Okay? So this part here is related to the quality criteria that we use and the element length. And then this one, compare the results with hand calculations. When we are dealing with complex models, usually we don't have hand calculations available, which is this case. So the only thing that we need to do is to check if sum of all forces is equal to 0 in all directions. Let's do this. I'm going to use this Excel spreadsheet. I'm going to put here fx, fy, and fz, right? And in here I need to calculate reaction forces. I'm going to teach you how to do this by using field output results, because I have shown to you how to calculate a reaction force by using history output results so far, right? But here in ANSA, in the first step, output requests, you see that in the field output requests, I also requested reaction force. Okay. All right. So first of all, in this part of the screen, right-click New 2D window, and then this is going to be named as window 2, and then here we have it as an empty window. 2D means that it's going to be used for plot. And right-click Create Curves from Model Entities. And then in here we can select a node, the node ID, and we can select between the results that we have calculated for field output. In the previous video, I have shown to you how to calculate the von Mises stress, these two, right? But I have calculated some other results. I'm going to talk about it later in this course. But you see that I don't have reaction force here because I didn't calculate it yet. So let's do one thing here before close this. Let's go to MetaPost, where I have this result, read results tab, and then results, and then a scalar, and then in here, reaction forces. And let's start with direction X. You should have this toggled so that when you click on read, you're not going to overwrite the other results. Let's now wait, it's calculating it. Let me also untoggle this option. I don't want to see fringe now. We are in the second step, 60%. You see that it's not so fast. Maybe also because I'm calculating this. 60% here. All right, it's almost finished. Let me see here. 18 minutes already. So time passes really fast. And I'm going to also request direction Y now that this is finished and read. Now, while it's reading direction Y, I'm going to select window 2 here. Window 2. Okay, now here I have window 2. And first of all, I need to get the ID of... Oh, actually, there is one thing that we can do here. Go to Create Curves, right-click Create Curves from Model Entities. I can select by node set. So I need to get the ID of each node that we have a constraint displacement. Remember that we can only calculate reaction forces at nodes where the displacements are constrained, so that we have the constraint equations to be used. So double click on constraint here in ANSA, and let's select this constraint and this one. And by the way, I have the peak mode activated here. Now I have these two constraints selected. I can right click and show only. Now double click on node so that we activate the node selection filter. Zoom in here, and then you see that the node ID that we have here is this one. Select this node, open this node card, Control C this node ID, and in META, Control V this node ID here, press enter. Now we have this node here. Let me click here to reset, and then press enter. Again, now we have only this node in this list. Now let me go back to ANSA, close this, zoom out and zoom in the lower node. Let's get this node as well. Double click and Control C the ID of this node. Control V the ID here. And now we have these two nodes. Guys, in this module, I have only let me now click on show all. For this other node that we also have a displacement boundary condition, I have only a displacement in the z direction. So in here, I'm not going to have a reaction force in the x direction because I don't have a displacement in the x direction applied there. So I have only at this node and this node. I'm going to select both. So hold the control button and select both. And then I'm going to select here this option, reaction force x direction, and then create. Close, and I have these two plots created. What we have here is exactly what we should have. You see, by the way, let me show you how to handle curves. You can use the scroll button to zoom in or zoom out. Hold the control button and you click the middle mouse button, that is the scroll button, to translate like this. You can click here on a fit in view to make it fit in view like this, and etc. So you see that this curve here has this reaction force like this, and we have this last value for the last increment of step 2. So I can double click on this curve to open this, go to the edit tab, and then you scroll down to get the reaction force at the end of the second step, this value. Double click to get this, and then I'm going to Control V here, right? And if I go to the name, name, you see that we have the node ID here, right? So this is the node ID. I'm going to put it here, node ID. And then we have this force here. In this case, it's in Newton. Now, close this, and then in here, double click on this one, go to edit, scroll down, get this last value, Control C, and paste it here. And let's go to name and get the node ID here, Control V. And that's all. Let's also create, we're going to have one additional column here for that other node, but this is going to be used only for FZ. So in this last one, I'm going to get here a total, and I'm going to sum. I'm going to simply sum like this. This one plus this one plus this one. And we have 0. Let me increase the number of decimal places here to 3. So you see that's let's see, status, then this is okay. You see that let me select everything and let's enter everything, and also let me create a table here. all borders. The sum of all forces in the x direction is equal to 0 as it should be, which is a good sign. Now let's see sum of all forces in the y direction. And by the way, you see in the x direction, on one node we have a positive force, and at the other node we have a negative force. And this is expected. If I get a view pressing F3, it's like we are having something like yeah, actually I can use this image here. We have something like if we have this force applied like this is trying to rotate this beam in the counterclockwise direction, right? And as a reaction, we should have a bending moment in the opposite direction. So that's why in this node, we have a force in the x direction in this manner. And in this node, we have a force in the x direction in this manner. So that this is a binary of forces that is going to generate a reaction bending moment in the clockwise direction. That is going to be equal to this bending moment. So that the sum of all bending moments is equal to 0 as well. You can check that. I'm not going to do this check. I'm going to do only for forces. Okay? So this makes sense, right? All right. Let's create a new 2D, window 3. We can right-click on this one and rename, and then say this is fx, and this one is rename fy. And for fy, we also have only those two nodes. So right-click, create curves from model entities. Here we have those two nodes, fy, create. And again, we have the same thing. One is positive, the other is negative, and eventually the value here is the same. Guys, let me go back here to read results. Results, scalar, and fz. And then in here, read. And then while it's reading, let's go to this tab again, fy. And then let's double click on this curve here. This is for a node that ends with 88. Edit gets the last value, Control C, Control V here. And now for this one. And then this is for the other node, Control C, Control V. Let's do the sum of all forces in the y direction, and then you see that it's equal to 0. And then the status is okay as well. And in here for this one, forces are equal to 0 in these two directions. This is in Newton. And this one is also in Newton. Yeah. Now in the z direction, we should also include this node, because we are going to have a reaction force here, obviously. So double click on constraint, select this constraint, open the card of this constraint, and then let's get the reference node of this coupling and copy the ID. Go back to META, close this, create a new one, 2D. This is FZ. And then in here, right click, create curve from model entities, Control V, the ID of that node here, press enter. Here we have it. I'm going to include in this selection using the control button. I have added this to the selection, and then direction Z and create. Close. And now let's start with this one. Double click on this one. This one is for a node that ends with 88. Last value, Control C, ends with 88. This one, Control V. This one is for a node that ends with 300. Last value, Control C, Control V. This last one is for this node. Let me put this column here. And then the value is equal to this. And then sum of all forces in this direction. And you see that we have a non-zero value here. So this means that the sum of all forces in the z direction is not exactly equal to 0. Remember that here we have a numerical solution of the mathematical model. So it's okay to, if a value is not exactly equal to 0. What matters is if this value is large if compared with the magnitude of load that we have applied. In this case, we should use the force that we have. For example, you see that we have 200,000 newtons here, and in here we have 163,000. So for example, if I compare equals this divided by this 200,000, press enter, and then let's transform this in percentage. This residual of force represents 1% of this load. So this residual of force is small compared with the magnitude of loads that we have applied. So it's okay to have this residual of force. Okay, so we can say that this is okay. 1% is small. All right. So guys, this is the verification of the mathematical model of the type BVP. This is a very, very important step. Let me see how this is going. Yep, it's going to take some time because, well, I'm not going to post-process the results of that analysis in this video. Okay, and now I wanted to show some additional stuff here to you. Let me see how much time we have yet. Well, we have a lot of time yet. 32 minutes. We have 30 minutes yet. I guess that in this video, I'm not going to have time to start building the second variation of this model. So let's go back to the meta post tab here, read results, and results scalar. Before I started this video, I have calculated some other results. So just for you to have the same thing as I have here, first of all, calculate equivalent plastic string. This equivalent plastic string is like a von Mises string. It's like a von Mises string for plastic string. So it's an invariant of plastic string. It's not like a plastic string in the x direction or y direction or z direction. It's like a combination of all these, just like we do with when we calculate a von Mises stress. Okay. So this equivalent plastic string can be compared with the stress strain curve that we have when we have these extracted from a uniaxial tensile test. Okay, when we learned about, we have learned about it in the nonlinear FEA course. When we have learned about plasticity, remember that in here we learned how to calculate, it was, let me see where we learned it. Yep, it was here, effective plastic strain. So here we have how this is calculated. In this case, we have it calculated in the incremental format. Okay, so this is an increment of equivalent plastic strain. All right. So I want to calculate it in the integration points and max of in, out. And then you should have this toggled and read. I'm not going to do this because I have this calculated here in this list. You see that I have this one equivalent plastic strain calculated already. Another thing that I wanted you to calculate is contact pressure. And then in here we can select the surfaces available, but well, you can select the surface here, which is the two surfaces that we have for the contact that we have defined, as 16 and as 17. If we go back to ANSA and search for contact pair, double click here, you see that the ID of the sets that we have used in this definition is 16 and 17. Okay, so select this one and read. Also, you can calculate, if you'd like to, you can calculate frictional shear 1, shear 2. There are two orthogonal directions. You can calculate relative tangential motion, contact status. For contact status, for you to be able to understand what is going to be plotted, you should check Abaqus User's Guide. So this is something that you should, this is a skill that you should develop. You should always keep the Abaqus User's Guide at hand for you to check. Okay. Contact opening. What I wanted you to calculate here is just this. It's okay. Just the contact pressure. Okay, so let's start analyzing the beam. We didn't analyze the beams yet, right? Let me click and show all. You see that I have the beams here, right? I wanted to see how the translator connector applies the bolt pretension in the beams, because we have used a translator connector, right? So let's see how this happens. So I want to, while I have the bolt pretension being applied, and also the displacement, let's zoom in this region, for example, and let's see what happens with the beam. So initially, we have this condition here, right? The beam is reaching to this position where we have the translator and the reference node of the coupling. Now, if we start going through the increments, you see that if I zoom in, look at what happens. Oh, so you see, I wanted my screen to follow this node. So right click, view, follow one node, and then select this node here to follow. Okay, now we can zoom in a lot and then start going through the increments. Look at what happens when we have the bolt pretension being applied. The beam enters the, well, it moves in this direction, and the translator is doing this. The translator is moving this node in this direction, and then this beam, and then because of that, we have some traction not traction, a tensile load occurring in this beam. The software is going to calculate the reaction force generated by this displacement until it reaches the connector load that we have defined. That is 155 kilonewton. Okay, so let's see. Here we are at the end of step 1. So this is the displacement that we had. And then at step 2, you see that this relative displacement is fixed because we have applied the connector motion. You see, I'm going through the increments of step 2, and this relative position never changes, no matter what. And that's what the connector motion does. Very interesting, right? Okay, so this is something that I wanted to show. Another thing is that, let's go to Tools, Settings, Drawing, Model Geometry, Line Elements, and then Draw Cross-Section, so that we are able to see the cross-section of the beams. Let's close. And then let's activate, let's select here, for example, stress, Vomis stress, this option, max in, out, show contour plot, on nodes, contour plot, could be like that. Now you see that we have this stress, the omissive stress, acting on each beam element, right? We can isolate the beam elements to analyze the stress at these elements using this function, not select by property ID. All beams have the same property, so we can isolate one of them, and then I'm going to end up selecting all of them, middle mouse button. And here we have this stress, von Mises stress for these beams. We can use this scale to analyze this stress. So you see at first, in the first increment, we have this stress very small, and then we start applying the connector load, and then this stress is increasing, and then we continue, and then this is the end of step 1. So at the end of step 1, we have von Mises stress equals 493. And we know that we have mainly a stress in the axial direction. So this von Mises stress is going to be very similar to the normal stress in the x direction that we have. We can also calculate this normal stress. In this case, we would need to request here stress components and normal x. I'm not going to do this because it's going to be a very similar result. And then when we start the second step, let's start it. You see that we have an increasing stress on the upper node, or on the upper bolts, because this is the region that we have a traction occurring, and here we have compression. So we have the stress decreasing here and the stress increasing here. And this stress increases a lot, as you see. It increases until 1000 MPa. If we go back to ANSA, material, list, bolt material, F2 in the plastic data, you see that the yield strength is pretty large for this bolt. This is a high strength bolt. And the von Mises stress that we have here is yet below this value, which is, I guess, the author wanted to represent the ultimate tensile strength here. So we are almost reaching the ultimate tensile strength. But we are below this value yet. If we had reached this stress, then the bolt would lose all its strength, because here we have this horizontal line. If we inverse here, we have this horizontal line, zero stiffness, and then we would have some instability occurring. It's like the representation of the bolt breaking in this case. But we would have to increase more the displacement. If you'd like to, you can try this. Okay, instead of applying 200, you can try to apply 250 to see these bolts losing stiffness. Okay, this is a good exercise. All right, one thing that we can do here is to amplify this multiplier. Let me go back to the... We can amplify this deformation to maybe 100. Press enter. And then let's see what happens when we have the bolt pretension. You see? The size of the beam increasing. This is the translator connector acting. And then we have this rotation. Here we have the deformation amplified too much. Okay, let's go back here and then type 1, press enter. Now we have a tree scale. All right, now this is what I had to show related to the beam. Now click on show all and let's hide the beam, because the stress of the beam is too large and it's messing up with this scale. So let's use the not scale, select by property ID, select one of these beams, and now it's not showing anymore. Now I want to calculate von Mises stress, max in and out, activate these, and then let's see the stress on the other elements. So look at how interesting this is. In the first step, where we have bolt pretension being applied, this stress is concentrated around the holes, as we should expect, right? And then here we have the end of the first step, and then let's continue. I'm using the scroll button to go through the increments, and then we have a different stress distribution when we have this displacement applied here, right? And then we have these happening, like these, and then buckling, and etc. What I want to show to you guys here is, since we have defined the material using a perfectly plastic material model, whenever we have yielding occurring at any material point, then this material point loses all its stiffness, which means that the force cannot increase anymore in this material point. The force is kept as constant. It doesn't mean that the force is going to be equal to 0. The force is going to be kept as constant, and the forces are going to be redistributed between other elements that we don't have yielding occurring anymore yet. Okay, so let's see this happening. Let's go back to ANSA, press ask, material list, and we have this material here that is used for most of the plates, except the end plate and this red one. Double click on this one, press F2 here in the plasticity properties, and then you see that the yield strength is 391. If I go back here to META, I can adjust this scale so that the maximum value is 391. Actually, we can define this one as 391. So double click on this one. Firstly, press ask to deactivate the function that was activated. Double click on this one and redefine it as 391. Press enter. Let's firstly start with this one, 391 here. Double click 391. Oh, sorry. 391, and then this one, 391. So let me try 400 and 391. Okay, now it worked. So everything that is orange in the model has the volume stress larger than 391 or equal, which means that the stiffness is equal to 0. But let's hide the end plate. So use this function, select by property, select the end plate, and also let's hide this plate that has a different yield strength. Press ask. Now let's check the colors that we have showing up here. So in these first increments, we don't have anything yielding yet, right? Now you see that in these increments, maybe we start having some region yielding here. It's orange, maybe here. So, for example, this material point has lost all its stiffness. The force that we have here is going to be kept constant. And then because of that, the forces in this region are going to be redistributed, and we're going to end up having more forces around the elements that has not yielded yet. Let's continue. And now we have all this region here with plastic strain. So we don't have a stiffness here. So this force is going to be redistributed for these elements around. And also here we have all this yielding and all this yielding. Let's continue. Oh, in this next one, everything here in this region has yielded. So you see that you see how important these stiffeners are, right? Because when we have this occurring, we lost all the stiffness in this region. So the forces are going to start increasing in the plates. Because, oh, sorry, this orange was not yet related to yielding. It is this darker orange. So let's disconsider everything that I have said. But the rationale is going to be the same. This darker orange, we start having some yielding here, here, and also here. And then these increases, many regions are yielding. And then when we have all this yielding, we have more stress being distributed for these stiffeners. Right? and then you see that this yielding region increases. But it doesn't mean that the structure collapses because we have some other regions that has stiffness yet. But at this point, this whole section has yielded. You see, most of this section has yielded. And because of that, we have collapse. And that's why we have this inflection point here. We have this loss of stiffness for the structure as a whole. Here we have the collapse of the structure, which is when we have this whole section with plastic strain, with plasticity occurring, and this whole section lost most of this stiffness of its stiffness. We do have some region here yet, but it lost most of this its stiffness. So I wanted to explain one thing here. We need to see the contact pressure for me to explain this. So let me see. 51 minutes. Oh my god. Well, we could perform this kind of analysis for the end plate. For the end plate, the yield strength is related to this other material. The yield strength is 263. So in here, let's redefine this as 263. Now everything that is orange has yielded. And I want to show all, isolate by PAD, select this one and this one, middle mouse button, return. And let's go through the increments. So at first we have this condition, nothing is orange. Now we have this first region yielding. And then we have all this region yielding. And anyways, we have most of this plate yielding. Okay, let's show all. And now let's analyze contact pressure. And by the way, guys, if you would like to have this scale calculated automatically, you can right click and select linear and auto range. Okay. And now there is just one last thing that I wanted to show. There is too many things to show here, but I wanted to show just one last thing. I have calculated here contact pressure for the surface S17 and S16. Select this one. And in here, let's go back to the first state. And let's go through the increments to see what happens. So at first we have contact pressure just around the holes. Notice that we don't have contact pressure on these two layers of elements because we needed to eliminate these two layers of elements in the definition of the contact because of that over-constraint issue related to this coupling. We are not going to have this is a problem. We are not going to have this issue when we get to model the bolts, nuts, and washers using solid elements. Okay? When we do that, we are going to have this region in the contact definition. So we're going to have something more realistic here, right? And this is whenever you want to create a mathematical model to represent a physical model, you should have in mind what is the result that you want to extract. If you want to extract this curve, moment versus rotation, and that's all, then representing the bolted connection in this manner is good enough. Okay? Because you see, we're not going to have something so realistic here, but that's okay. This is not going to impact so much in the extraction of this curve. Now, if you're interested in calculating the stress in this region, or where you have the bolted connection, then you should consider a more detailed model or bolted connection strategy using solid elements. Okay, so my point is, whenever you're building a mathematical model, you should have in mind the result that you want to calculate, and then based on that you're going to make your assumptions. You're going to simplify some regions that you can, and you're going to detail more some regions that you need. Okay, so this is very important. Anyways, let's continue. So the pressure is in this region, and then here we have the end of step 1. You can see here in this title, 1. And then we have the beginning of step 2, and then you see that this pressure starts to be distributed in a different manner. We have some compressive pressure here in the stiffener and in the beam flange. And on the top side, since we have this beam flange, pulling this to the left, then we have a gap opening here, and that's why I don't have contact pressure. Okay, you see that if I move to these increments, you see that we have a gap opening here, so we don't have contact pressure. But we do have some contact pressure on top here because of this movement that is happening, you see? While we have this moving to the left, we end up having this moving to the right. It's like a lever. And in here, we have this compression occurring like this. Okay, we can isolate the end plate by using the not function, select by PID, middle mouse button, and then we have it isolated, and then you can analyze how we have the pressure being distributed through the increments of this analysis. And now what I wanted to explain that is extremely important, and this is the last thing that I wanted to show. Notice that in the beginning of the second step, we had only some pressure here and here, because you see the beam flange pushes this region, right? When we have this force in the downward direction, we have some bending. We have some bending here in the counterclockwise direction, and we have some. When we have some bending, we have a compression here and traction here, right? This is something that we know. Where we have compression, let me isolate the end plate again. We're going to have this compression being accumulated where we have the stiffener and the beam flange. But the thing is, you see that we start having some pressure here where we have the beam web as well. And this happens because in this increment, probably we have the beam flange yielding, so it lost its stiffness, and then we cannot have any additional increase of force in this region. Probably in here we, if we calculate the von Mises stress and establish this limit as 391, we have many regions here yielding, as you see. And then the force in this region cannot increase so much anymore. So the force starts being redistributed, and then we start building some force in the web as well. And that's why, let me isolate the end plate. Let me just auto range here. And that's why when we go through the increments, we start having some pressure building here because of this force redistribution, because the web hasn't yielded yet. So we can have some increased force in the web as well. So this is very interesting. And this is what we should have occurring here. All right, let's see. 1 hour. Guys, there is a lot to be shown here, obviously. But I guess that I have shown, there's just one additional thing that I wanted to show, actually. Let's hide the beams. Use this function, PID, select one, press ask. Let's go back to the first step, and let me deactivate the fringe. And I want to see only deformation. And I'm going to increase this deformation by 100. 100, press enter. Now zoom in here and notice what happens when we have the bolt pretension. When we have this bolt pretension, let me go through the increments. Look at what we have. Since we have this putting this reference node in the positive x direction, we end up having this force being distributed among the slave nodes of the coupling, and then we end up having this happening. But this is happening because in this region we don't have contact defined. So what is happening here is not so realistic, you know. We are not going to have this happening in this exaggerated manner. Obviously that we are amplifying this by 100, but we are not going to have this happening in this exaggerated manner when we model the bolts, washers, and nuts using solid elements. Okay. All right. So yeah, as I mentioned, there is a lot to be shown here. You can study these results as much as you want. You should do this to practice. You can analyze equivalent plastic string as well. This one is, I forgot, let me put a multiplier equals 1. Yeah, you can analyze the regions where you have plastic string. I guess it's even easier, right? So in the beginning, we don't have any plastic string occurring. You see, there is no plastic string. And then we start having some plastic string here on this second step. The plastic string starts in the stiffeners and in this region, as we saw. And also here. And then let's continue. And then you see the plastic string distributes like this. Let's continue. Now we have all these with plastic string. Let's continue. Yep, and that's how we have the plastic string distributed. Obviously that this value of plastic string here is not something that we can use because of the way we have modeled the material using perfectly plastic material model. But if you had used a true plastic versus true plastic string versus true stress extracted from a uniaxial tensile test, then we could use these results of plastic string. But this is not the case in this situation. All right. All right, guys. That's the end then of this video, and then in the next one we are going to start creating the second version of this module. I don't think we are going to have so many videos after that. I guess that in total we're going to have like 15 videos. It's much more than I thought, but I guess that at least you're learning a lot by going through this tutorial, right? You're learning valuable things that you are going to actually use if you get to work in this industry, or if you are already working in this industry. All right, so I hope you liked it, and see you in the next video.